Power amplifiers. Hi, I'm Dan. My goal is to demystify technology and bring more understanding to it. So in this video, I'm gonna tell you a little bit about the power amplifiers. Where they can be used, what they are, and some practical applications of the power amplifiers. So what is the power amplifier? Imagine that you have a signal. For example, you want to drive a AC motor or speaker. Only that you have is a signal that has a small amplitude, and if you connect some bigger load to it, the signal just disappears. This device like here is a general purpose power amplifier like this one. So what the power amplifier does is amplifying the signal and adding some power to it. With power added to the signal, it can drive something like a motor or a speaker. Power amplifiers can be divided into three main classes. Class A provides the less distortion, but is the most power inefficient. Its average efficiency is always below 25%. Class B is more efficient with efficiency up to 70%, but for better efficiency there is a cost, higher distortion. Class C, the most efficient power amplifier with efficiency up to 80%, but it provides high distortion that make it unsuitable for amplifying low frequency signals. It is mostly used in radio frequency applications. Let's start with Class A then. This is, let's say, the oldest one. It's because when first active elements like vacuum tubes or first transistors came in, engineers had to make optimizations to save money as those components were quite expensive back then. The principle of Class A is that transistor is working always in active region and amplifies the whole signal. Working point of transistor that is working in the Class A is set to middle of the active region, where most of the power loss occur. This makes it the most inefficient for signals with low amplitude. Because of poor power efficiency, Class A power amplifiers are used only for low power, like for example preamplifiers in audio applications. Principle of Class B is transistor amplifies only half of the signal. Because of it, it works in two regions, active and cutoff region. The most of the power loss again appears when signal approaches middle of active region, but because working point is now set in cutoff region, signal only is in the middle of active region for a short amount of time. Pure Class B cannot be used in audio applications due to high distortion, but it can be used where high distortion is not a problem, like for example driving engines or transformers. The last main class is Class C. It provides the highest efficiency of the three, but it has the biggest distortion. Principle of this amplifier is that it amplifies only small part of the signal. Because of that, it's not suitable for any low frequency application. It can be used in high frequency applications, as there you can simply filter any distortion. This is the principle of Fourier series, which tells us that all signals can be described using sine waves. In radio frequency, you mostly operate in pure sine waves, so you can simply filter all the remaining harmonics using filters, and still having pure sine wave on the output, even if transistor completely distorts the signal. Class A, B and C are the three common classes, but you can have a variation of it. Before era of high-speed switching transistors like MOSFETs, there was need for a high power amplifiers that have a small distortions. Engineers figured out that adding features from Class A and Class B, you can have an amplifier that has a small distortion like Class A and high efficiency like Class B, then higher power output. And this is how Class AB push-pull amplifier was born. Another variation is Class D. As I said before, the most of the power loss comes with the active region. So if signal will stay most of the time in cutoff region and saturation region, it will get almost 100% efficiency. It will be always almost 100% because signals always will have to get through active region, and that will add some power loss. In modern Class D amplifier, most of the power loss comes from the internal resistance of the transistor, as high transistor switching frequency makes it that power loss from active region is close to zero. Power amplifiers have many applications. We will discuss here only an electroacoustic power amplifier, as it has all features of typical power amplifier. Typical power amplifier is made of three stages: differential amplifier stage, voltage amplifier, and current amplifier. The differential amplifier stage is the first stage of the power amplifier. It compares two signals, the input one and the output one. But the most important job of this stage is to automatically set working points of the transistors in the amplifier. The voltage amplifier stage comes next. Its primary function is to increase the voltage level of the signal received from the differential power amplifier stage. This stage provides high voltage gain. Finally, the current amplifier stage. This stage is designed to increase the current capability of the amplified signal. This stage provides high output current, low output impedance, and is capable of driving low impedance loads such as speakers. This is the part of the whole power amplifier that adds power to the signal, as I mentioned before. This is of course just a brief explanation of the power amplifiers. There is more variation of it. Amplifiers that are designed for different applications can be different, but the general power amplifier that I described here can be used in any applications that requires power amplification. That will be everything for this video about power amplifiers. This is just a brief explanation, as I said before, but it's a good start. I hope you like this video about power amplifiers. Don't forget to give me some feedback about my videos, and see you in the next video.